Hello everyone. Today let's take a look at the blade element momentum theory of a rotor dynamics. Once again, let's take a look at the blade element momentum theory of a rotor dynamics. Let's assume today from the schematic we have a steam tube and inside it a rotor, and let's assume that this section is called A, section A, and this section is BC, and this section we have D. And also at this section we have the pressure A, PA, and also we have pressure B and pressure C at the section of the rotor blade, and we have PD. Also at this section we have UA and we have UBC and we have UD. Don't let us forget the thrust. Imagine from the rotor, which is T, and don't let us forget at the section of the rotor blade we have separate UB and UC. Based on the assumption of the equation of the momentum of a rotor. Now that we have a fully developed schematic for this today lecture, then we can deduce our thrust. Equals to T equals PC, that is pressure at C, minus PB to the area of a rotor ABC. Don't let us forget that rotor area ABC equals pi r squared. So therefore, our fully developed equation becomes thrust equals P C minus P B pi r squared. Also, don't let us forget that the thrust equation to the momentum equals the mass flow rate to the variation of the velocity entity, ud minus ua. Now that we have all this equation, the next thing is to put them together one by one for the full analysis. So therefore, T equals m ud minus ua. And don't let us forget that ub always equals uc from the theory of momentum assumption. Assumption theory. ub equals uc, which equals to ua plus induced velocity v1 and ud equals ua plus v2, that is the induced velocity at section 2, and also the pressure from the entry equals the pressure at the outlet, that is PA always equals PD. Now that we have all this momentum theory assumption, for rotor dynamics, in which we will need them later on one by one. Now let's assume we break the rotor steam tube into two sections or two regions using Bernoulli equation. Bernoulli equation always states that half rho v squared plus p equals constant. Now let's assume region 1. Region 1 is sectioned in such a manner in which we have A, and we have B, and we have PA, and we have PB. Don't let us forget we have thrust tending towards this part, and we have the entity of the velocity UA and UB. So therefore, using this region 1 Our Bernoulli equation becomes half rho US square plus PA equals half rho UB squared plus PB. Also, from region 2, which is the last tip of the system, where we have C section there, we have D, we have PC, we have PD. Also, we have the UC here and the UD here. And don't let us forget the thrust happens at this section of the rotor blade. Then we can deduce from the schematic using the Bernoulli equation that half rho UC squared plus PC equals half rho UD squared plus PD. Equation 1 and equation 2. Now we can single out PC and PB out of the equation. So therefore, we have our PC equals half rho UD squared plus PD minus half rho UC squared. We also have our PB to be half rho UA squared plus PA minus half rho UB squared. And don't let us forget that PA equals PD and UB at the rotor equals UC. Now we can single-handedly eliminate this due to the assumptions, and also this due to the assumptions. Now the equation we have left becomes equation we have left for the PC minus PB equals half rho UD square minus half rho U A square. And don't let us forget also from the assumption that the UD equals the summation of UA plus the induced velocity at section 2. So that means UD equals UA plus V2. Then we can slot in the equation to the one we have here. So our PC minus PB equals half rho UA plus V2 squared minus half rho UA squared so our PC minus PB equals half rho UA squared plus 2UA V2 plus V2 squared minus half rho UA squared. And this goes out as they eliminate each other. So our PC minus PB equals half rho 2UA V2 plus V2 squared then our PC minus PB eventually becomes 2 rho 2UA plus V2 V2 and don't let us forget our thrust equation becomes thrust now become half rho using this equation half rho 2UA plus V2 V2 multiplied by the area, which is pi r square for the rotor. And this is a very important equation that we will need later on. Thrust which is a truss entity. Now, let's derive the time derivative of both sides of the equation. Then, by deriving both sides, we can differentiate d as a thrust over dt equals d m, that is the mass flow rate, u d minus ua all over dt. And this eventually becomes thrust equals dm over dt becomes ud minus ua. Now the next thing is to derive the mass flow rate equation. And let us forget m dot equals rho a ua equals rho ab ub equals rho ac uc equals rho ad ud. And this is a mass flow rate equation entity. And also don't let us forget the rotor disk. The rotor disk area, that is the area BC. The rotor disk equals pi r squared. Now that we have all this equation, then we can single out the equation from the thrust once again from what we have, which is rho pi r squared for the section UB, that is for the rotor UB UD minus UA. And don't let us forget from the assumption once again from the assumption that UB equals UC. And also UB and UC equals UA plus induced V1, induced velocity V1. So therefore, UB equals UA plus V1, and also UD minus UA equals V2, and eventually V2 equals UD minus UA. So these are the major assumptions we need to justify all our equation of the rotor dynamics momentum equation. Now that we have all these our assumption theory equation, then we can slot in the value to the thrust, which is rho by r squared UA plus V1, V2, that's equation 1, and also from the previous thrust that we find, which is half rho 2UA plus V2, V2 pi r squared, and this eventually becomes rho pi r squared UA plus half V2 V2, and T2 now becomes rho pi r squared UA plus half V2 V2, and this becomes equation 2. Now by comparing equation 1 and 2, we can deduce that this goes, this goes, this goes out. The only one remaining is a V1 and the half V2 here. Now we can deduce from the comparison or juxtaposing the two thrust equation of the rotor dynamics that V1 equals half V2, that's the first equation, and also V2 equals 2V1. Now the final thrust equation now becomes rho pi r squared UA plus V1 times 2V1, which eventually becomes 2 rho pi r squared UA plus V1 V1. And this becomes the major thrust equation. For the rotor dynamics momentum equation. That is TR equals 2 rho pi r squared UA plus V1 V1. Thank you very much for staying tuned.